Okay, so all sugars will have the form some carbons and the H2NON, so a ratio of 2 to 1 between hydrogen and oxygen. Okay, it'll help you remember the formula. Okay, so you can see that single ring sugars, remember that ring is carbons. So the main one that we talk about is glucose here. And it has a certain structure. You don't need to remember it, but please remember that formula or a little trick to pull it out during exams, okay? You'll notice that the other monosaccharides have the same formula as well, okay? C6H12O6. Now, fructose, galactose, and glucose are different sugars. Notice how they're just structural isomers of each other, okay? Same atoms bonded in different ways, okay? Disaccharides are two-ring sugars. Sucrose, which is usually what we call most sugars, so the sugar that you put in your tea, is glucose and fructose bonded together, okay? And when they bond together, see they have this oxygen link, they drop out some water. So when two of these monosaccharides come together, they'll bond together, and it's a condensation reaction because it gives off water. And we'll talk more about that soon in a chapter coming up. Okay, when glucose and galactose bond together, we get lactose. Okay, you also have polysaccharides, which are just many ringed chain sugars. You got starches. Oh, and I've just got another form of starch there. Okay, so two forms of starch. Oh, one of them's just upside down. Look what I did there. I put glucose written upside down. All right. So some sugars consist of single rings, double rings, and a polymer of rings. A little bit more detail on that in our polymer chapter, not too much. Main thing is C6H12O6 for that glucose, okay? Okay, what does the yeast do? The yeast is for breaking down those rings, okay? And also the double rings as well, the disaccharides. But they have trouble with polysaccharides. They're not going to do it, okay? If you hope to ferment starches and other polysaccharides, you're going to need an enzyme, fancy biological word for a large molecule that breaks things down, and you add it to the fermentation mix. So you can do it. The enzyme breaks the bonds between the rings, they have a fancy name there, and they make it into a lot of monosaccharides, and then the yeasties go about their fermentation. All right, conditions for fermentation. We've talked a little bit about them. So you need yeast as a catalyst. Let's talk about temperature. You need a low temperature, less than 30 degrees, because you're using enzymes from the yeast, and at higher temperatures, these will unfold and they won't do their job anymore, okay? Fancy biological word is denature, okay? At higher temperatures, so they'll unfold. Some alcohols and some yeast even need slightly lower temperatures than that, okay? So if it gets too high, those enzymes are going to unfold and not do their job, and then the yeast won't do their job, and the whole thing's not going to work. A pH. It needs slightly acidic. 6.1 to 6.8 is a general range, okay? Outside this range, also, if it's lower or higher, more acidic or more basic, those enzymes are going to denature as well, and you won't get any fermentation. As we talked about before, you need anaerobic conditions because the O2 will oxidize the ethanol into ethanoic acid. So usually, an S-bend containing water, so this is an S-bend because it goes up and down and up, and you put water in there, and what ends up happening is oxygen can't get in, but CO2 can bubble out, okay? And so you don't get pressure building up and explosions. You also, the last condition that you need a low alcohol content, okay? Think about what alcohol does to living things. We use large concentrations to preserve it and kill it and stop it from doing stuff. So as soon as the alcohol content through fermentation gets to a certain level, it's going to prevent the yeast from growing and living, and it's going to kill them off. Usually, just a rough guide at about 14% volume to volume concentration. Alcohol larger than that is not possible through initial fermentation processes, okay? So if one thing that you can do to prevent it from getting so high is, without opening it up and letting oxygen in, add some more water in to keep it below that level, okay? Alcohols do come in concentrations greater than 14%, but what usually happens is that you do a distillation process to get rid of the water, and you'll be doing that to get rid of the methanol anyway, okay? So that's how higher concentrations of alcohol are made. Afterwards, a distillation process. Okay, what's next? Oh, I think that's all the theory. Let's do some examples. So structural equation for the addition of water to methyl propene. All right, meth, eth, prop, and we need a propene, and we need a methyl. The methyl must go in the middle position there. All right. Should I? Oh yeah, I should put my hydrogens on, shouldn't I? I shouldn't be lazy. The middle one's got 4 bonds. 2 there and 3 there. So there's my methyl propene. And we're going to add water. Okay, adding water. You need dilute H2SO4 sulfuric acid for it to work. Okay. So that initial bond is dropping down to a single bond. Let me put my hydrogens over here because they're not being affected. Also, this methyl group is staying the same. Okay, and so, oh, I didn't think about Makovnikov. I need to think about Makovnikov. So the hydrogen's going to go to the side with the more hydrogens. This one had 2. Okay, so it's going to get a third, a new one there, and the alcohol group is going to go on the second position. So the stuff that came, so the OH came from the water. Why am I erasing it? So that's the OH from the water, and that's the H from the water there. Okay, so what do we got now? We have got, oh, what am I doing? I don't want that. Go away. I've got a meth eth prop, a propan-2-ol, and a 2-methyl. Well, actually, we don't need a number on the methyl. It's just methyl prop, and we need a 2 on the alcohol because it could go anywhere on that chain, or it could be on the 1 position, actually. Can't go anywhere. Could always be on the 1 or 2, so it's methyl propan-2-ol. Okay, structural equation, let's do a substitution reaction between water and 2-chloropropane. So we're making an alcohol here from 2-chloropropane. Prop, 2 chlorine position, and we're adding water. Oh, it's a substitution reaction, so we do not need a catalyst. I'm pretty sure about that. Let me just check. Oh no, we did need a catalyst to go that way, didn't we? We did need a catalyst. We did need the same catalyst. Dilute H2SO4. You don't need a catalyst to go the other way though. That's right. So we need dilute H2SO4. And so we're going to keep our backbone. And instead of the chlorine, we're going to have an OH. And we're going to have HCl left over. Should I put my hydrogens in? I should be good. 1, 2, 3, and then 1 here, and a CH3, and a CH3. Cheating. Alright, so you've got enough knowledge now to do production of alcohols, and there's some check your understanding questions too if you're still struggling. Oh, and the last bit we need to talk about is biofuels. Okay, thanks guys.